a brief introduction for the magnetic effects of electric current. A charge at rest produces an electric field only. This we have studied in our very first lesson of electricity, electrostatics. A charge in motion produces both electric and magnetic fields. A charge at rest could produce only electric field, but a free charge in motion, not in a conductor, a free charge in motion could produce both electric and magnetic fields around it. But a current carrying conductor produces only magnetic field around it, no electric field due to a current carrying conductor, since a current carrying conductor is electrically neutral. When a conductor is carrying current, even though the electrons are flowing through this conductor, as a whole the conductor is electrically neutral. So there is no electric field due to a current carrying conductor. Only magnetic field is possible around a current carrying conductor, and that was confirmed by Ørsted by a simple accidental experimental discovery it is. So Ørsted found that a magnetic field is established around a current carrying conductor. And now we study various phenomenon and various parameters with the magnetic field due to a current carrying conductor, and it is determined by different laws, Amperes, like Amperes Law, Biot-Savart's law, etc. So we study. Now let us study Amperes Law and Biot-Savart's law. So first let's take up Amperes Law. The line integral of the magnetic field induction about any closed loop around a system of current carrying conductors is equal to the product of the permeability of the medium and the net current enclosed by the curve. The statement of Amperes law says that, more elaborately called the Amperes Circuital law, it is the line integral of the magnetic field induction about any closed loop around a system of current carrying conductors is equal to the product of the permeability of the medium and the net current enclosed by the curve. The mathematical form of the Amperes Circuital law is the line integral of B bar dot dl bar over a closed contour over a closed path is equal to mu naught times of the net current enclosed by that loop. Here is the integral of B bar dot dl bar over a closed contour, closed loop, is equal to mu naught into sigma I. In calculating the net current, the algebraic sum of the currents is to be considered, taking in reference to the plane about which the loop is considered, taken outward currents are positive and inward currents are taken negative. Around the system of current carrying conductors, we are going to take a closed loop, and the closed loop reference plane, if you consider, in respect of that reference plane, the outward currents are taken positive and inward currents are taken negative. And any current outside the closed area is not included in the net current. Only those currents which are bounded by our referred closed loop are to be taken in calculation of the net current. The Amperes law is analogous to the Gauss law, what we have studied in our electrostatics. That is, integral of E bar dot ds bar over a closed loop is equal to 1 by epsilon naught times of the net charge enclosed. This we have done in our electrostatics Gauss law. And here the Amperes law is just analogous to Gauss law in electrostatics. And the Amperes law is useful only when the closed path is symmetric with known limits. In Gauss law also we have studied that. The closed loop is to be selected in such a way it is symmetric with known limits. Here also we have to apply limits now. That's why for linear conductors, where the closed loop about which will be a concentric circle with the limits can be known now, 0 to 2 pi r, where r is the radius of that circular loop we choose. So such symmetric closed paths with the known limits have to be selected so that the Amperes law application becomes convenient to us. So Amperes law is useful with that limitation only when the closed path is symmetric with known limits. So we have some numericals on this concept and we take up those numericals.